Hey there! We're about to look at something pretty neat. We're about to show that just with our understanding of Newton's laws of motion and the empirical relationship, the ideal gas law, we can understand exactly the meaning of temperature. Now, you may know that temperature is one of the 7 standard units defined by SI Bureau of Weights and Means. These are the 7 quantities that you can measure in science to determine everything. Temperature is defined to be one of them. But what is temperature really? Is it something more basic? Is there something more basic than the unit alone the temperature can be defined as basic as mass, length, and time? Well, it turns out there is. And in showing so, we're going to also get an idea of why we actually have to define this other quantity, temperature, as a separate base unit. Well, that'll become clear hopefully as we go along. But anyway, so what are we gonna do? Well, let's see here. That's good. We have ideal gas law. Pressure times volume is equal to the number of particles times Boltzmann's constant times the temperature. Here, maybe I'll write KB right there. It's supposed to be KB. Could write it either as K or KB, depending on the mood. We're going to look at the ideal gas law for an L cubed box of ideal gas. What do we mean by L cubed? Each side of this box has a length L. Two sides we can see, and the hidden dimension coming in and out of the screen. So we're going to consider ideal gas for an L cubed box. Let's take a look at our L cubed box. There it is. Nothing's in it, so there's no pressure and no temperature. Let's put something in. 50 particles. That's creating pressure right away. They're at 300 Kelvin. We got about 6 atmosphere of pressure. We see the average speed here is about 1200 meters per second, and some of the particles are moving faster, some are moving slower. Together they're creating the pressure and evidently the temperature, since we had to put something in there for that. Put in another 50. What happens? Temperature stays the same, 300 Kelvin. Average speed's about the same, 1200. Pressure doubled, as you see. Another 50. Temperature the same, average speed the same. Pressure tripled, and so on. Now we're up to 200. Again, you see, so here's our distribution of speeds, also our distribution of kinetic energy. Average speed's the same, and temperature's the same. Pressure, or now at 4 times the pressure that we originally started with. So, okay, well, what's causing the pressure? Obviously, the particle bouncing off the walls. So what's the temperature? Well, it's something. With the ideal gas law, do we know that pressure will go up when we increase the number of particles? Yes, we do. With everything else held fixed, PV equals NKT means the pressure is directly proportional to the number. Now, with everything else held fixed, pressure will be directly proportional to the temperature? Yes, absolutely. Let's heat this up. What happens? We're heating up our gas, the pressure is going up, the temperature is going up. The pressure clearly went up. What happened to the average speed? Average speed went up. Yes, it did. So the pressure went up, The average speed went up, the temperature went up, the number of particles did not go up. So what does the temperature have to be some sort of measure of? Well, it has to be some sort of measure of the average speed. Yeah. Or actually, maybe it's a measure that has to do with the average speed. What might that be? The average kinetic energy. That's what we're about to find out. Show that in an ideal gas, temperature is proportional to the average kinetic energy, right? And what is kinetic energy? Kinetic energy is the 1/2 mv squared of the particles. That's their kinetic energy. 1/2 their mass times their speed squared. And if we're going to talk about average, then we're going to be talking about average of this. And actually, if the masses of the particles are all the same, and you can see they are in here, these particles, they don't chemically react because in ideal gas, particles are not allowed to react or do anything like that. So they just stay as fixed, hard little balls bouncing off the walls, and the mass will stay constant. So this will end up being 1/2 m times the average speed squared. Let's assume right now we don't really know where the temperature is coming from. It's just recorded by this thermometer. We have some idea what it is, but we also feel we can't derive it from first principles. Is there something we could derive from first principles? What about the pressure? We know the exact definition of pressure is force per area. And we can see that these particles are causing a pressure by bouncing off the walls, therefore exerting a force, and the walls have some sort of area. So there's a force per area certainly associated with that. Do we have some chance, and we could add more gas in, and we can see that we add more gas, there's more pressure, and the pressure in the box must be due to some sort of average force, average pressure, bounciness of all the particles exerting on the walls. What does it depend on? Does it depend on collisions? Let's see, the pressure is about 24 atmospheres here. Take away collisions. Pressure doesn't change, temperature doesn't change. So whether or not the particles are just zipping across from one side of the wall to the other and then having a completely elastic collision, an energy conserving collision with the walls, or they're having completely elastic energy conserving collisions with each other, doesn't matter to the pressure. So in other words, the ideal gas law will hold in either case. So this means then, what does it mean? It means that we could study just the motion of a single particle, right? Find the pressure owing to a single particle, and then what? Just add once we understand what one particle does, we can understand what n particle does, right? Because then the pressure will be what? Just be basically n times the pressure of one particle, right? But on average. So let's consider that. So we want to just bump down. I want to just get nothing. Let's just consider the pressure due to one particle. There it is right there. It's bouncing around and it will exert a pressure. So here we're going to just consider the pressure due to this one particle bouncing along. Let's consider what happens. The particle comes out here at the pump, travels along till it hits the wall on the left here. The wall exerts a force F on the particle, turning it around in a completely elastic collision, meaning it has the same speed or conserves energy coming in and going out, travels across the chamber again, hits the wall there, force turns it around, Then it comes back and arrives again at the left wall, the wall we're considering here, where the wall exerts a force F on the particle right there again, and turns it around. This force F is the same as this force F, of course, to turn the particle around. But we want to know the pressure. Well, the basic definition of the pressure is that it's force per area. Okay, so great. Well, the area, what will that be? Well, we know what the area will be. The area will be L squared because we have an L cubed box. But what's the force? Well, from the basic definition of force, we know that force is the rate of changing momentum, how much the momentum changes over how long it takes that change to happen. And here we said this force is a force all in the x direction, right? Because that's all this wall can do is exert a force in the x direction here. It can only exert a force perpendicular to the surface of the wall. So here this P is standing for momentum. So this is a change in momentum. There's a momentum over the time it takes to make that change. And this P standing in for momentum is what? P for momentum. P is mv. So can we figure out what the change in momentum is? Let's look at what this collision does. If we define this direction to be the x direction, conveniently, because that's all we want to consider is just this wall, which has a normal surface facing along the direction of this force, which is the x direction. What's the result of the collision? This particle has velocity components vx, vy, vz, because we're talking about 3D. But if you go back to chapter 2, way back there, we learned that you can simplify the dynamical motion of any object by just considering its motion in the Cartesian component dimensions. Each 1D component of the motion describes the motion in that component direction. And then we just take the complete motion to be the sum of the motion in all the directions. So here, if we look at what happens at the wall, the only component that gets changed is the x component of the motion. And that just gets turned around to be the opposite of whatever it was. So remember, so here we have P is standing for mv up here. A little bit confusingly, it's standing for pressure up here, but that's just something we're going to have to deal with. Can we figure out this pressure force? Well, can we figure out what the pressure force, which only is an x component of force, is going to be the change in momentum over the change in time. And since that force is only in the x direction, we only have to worry about the change of momentum in the x direction. So could we figure out what that is? Well, yeah, if, say, we know the mass of the particle, then the delta P will be equal to the mass of the particle times the change in velocity, right? P is mv, the mass doesn't change, so the change will just go with the change in velocity. So that will be the final velocity in the x direction minus the initial velocity in the x direction. Change final minus initial. And here we can see this is the final, so that'll be Vx is the final, and the initial is this one is a minus x, right? Because it's traveling to the left, which we're calling that the negative direction. So minus a minus is a plus, so that'll be plus Vx. And we see our change in momentum is 2 mvx. Now, what about the time it takes for that change to happen in? That's the contact time of the particle on the wall, the time when the force is being exerted. Very small. Do we have a chance to measure that time? Well, let's look at our particle. All right, so I've got this timer right here. I could turn that on and see could I possibly measure the contact time? I don't think so. But maybe what could we measure? What could we measure? We're talking about collisions with this wall. Why don't we measure the time it takes between collisions with this wall and see if we can hope to measure that? I'll start the clock right there. Okay, so that was one collision. Then we'll go ahead and stop the clock once it hits that wall again. Stop the clock. Okay, it said 18 seconds. All right, we'll see. Try again. Start the clock. And it's going to cruise around. Stop the clock. 18 seconds again. So we could see, and you can see from the uniformity of the motion, that it's always going to take the same amount of time for the particle to make a round trip. And every time it makes a round trip, that force will come back on when it hits the wall. So what we're going to do is use that to figure out what the average pressure force is. In order to get a handle on the average pressure force, we're going to need to turn to the idea of impulse. So we can see the particles going back and forth across the chamber with complete regularity, and every time it hits a wall, an impulse force turns on just for a split picosecond to turn the particle around. So we can picture that situation like this. So here's the force exerted by our left-hand wall, and it turns on just for a very small fraction of a picosecond right there. Delta delta T sub s. That's the contact time with the wall, and then right then the force cranks up to its maximum value, F. We can just picture it like this: just turns on, boom, just briefly for a fraction of a picosecond, until when does it come back on again? So we could say, well, here it first turned on, say at 18 picoseconds, like we saw, turns the particle around, particle makes a round trip, so it'll be back here at time 36 picoseconds, and so on, 54 picoseconds. The particle will be back here again. With the idea of impulse, what can we do? We could actually look for the average force that the wall could exert over an extended period of time to get the same change in momentum. So here the idea of impulse is that you have I as the impulse, gives you a change in momentum, and that's equal to the average force over some time, some average time of the impulse. Okay, so what's that average time we want to use? Well, I think it's pretty clear that average time would be the time we could get some handle on here. That's going to be these delta t's right here. There's this delta t, this big delta t, and we can see in this case what those are. There's delta t, there's delta t right there. Each one of the delta t's you can see in this case is 18 picoseconds, the time it takes for a round trip to hit that wall again. So what we want to consider then is the force that, if it was exerted over this longer time, would bring the same impulse, the same change in momentum. So we could say there'd be some force, if we just kept it on all the time, it would exert, and here it's a constant force, right? It's just on all the time. Just keep it on. it will do the same job, right? It would slowly turn that particle around and give it its change in momentum. And so this force, right, that's basically going to be equal to the big force times that small change. So to find the average pressure force, we use the idea of impulse. And then to find the average pressure, that is going to be given by the average force over the area. And here the average force is going to be the change in momentum, which we know is 2mvx, over the time between collisions with the wall, which now we need to figure out. We're close to figuring out the average force. It's the change in momentum over the change in time. The change in momentum we have right there is 2 mvx, change it 2 times the change of velocity in the x direction, or what is the change in velocity. The time, well, we know that's the time between collisions with the left-hand wall. So now we just have to figure out what that is, right? I mean, we're going for, well, we really ultimately, we're trying to show that the temperature is proportional to the average 1/2 mv squared. So here we're seeing we got an mv right there. That's great. Now, so this delta t guy, okay, well, we measured it with our timer. And so for this one case, it's about 18 picoseconds travel time, round trip. But could we get it from first principles and get it in terms of something related to what we're going for here, the kinetic energy? All right, let's have a look. So remember, speed in any component direction is equal to how far you go, the distance, over the time it takes you to travel that distance. Distance over time. So here we're going to be looking for the speed in the x direction, right? We could just consider, just get rid of that. So here we can just consider the magnitude of the velocity in the x direction, right? We see that changes signs, but the speed always stays the same. Actually, the speed of this particle stays the same in every component direction. It just changes sign when it hits a wall. So when it hits this wall, it changes sign in the x direction. All right. So with that in mind, let's see. We're talking about a round trip here in the x direction. How far does the particle travel in a round trip? Goes across in the x direction. Goes across once, right? So this is like the change. This is like the distance in the x over the time. And that time that's actually the delta t. That's the round trip time. How far does it go in the x? Well, it goes L going this way and L coming back, right? So say here it's going to go L, then it's going to come back and do another L to get back and hit again. So, and then here we could just blow off the absolute value. That's 2L divided by delta t. Knowing that the velocity in the x direction is 2L over delta t, we can solve for the delta t. It's 2L over bx. Now we have that. Put that in over here. So the force, delta P over delta T. You know the delta P, 2mvx over delta T. The delta T we now know from before is 2L over Vx. And here, 2 cancels with 2. Downstairs, downstairs goes upstairs. So our average force, average pressure force, is mvx squared over L. Now we're looking for the pressure, or the average pressure. The average pressure is the average pressure force over the area. The area, well, we're talking about an L cubed box. So the area of any face is L squared. So the pressure is force divided by area. Here's the force. We just solved for it, mvx squared over L. And then all we have to do is multiply that by 1 over L squared is the same as dividing by the area. And that bumps the L up by another factor of 2. So now it becomes pressure force is mvx squared over L cubed. And what's the L cubed? Well, that's actually going to be the volume of the box. That's actually mvx squared over V, right? Because volume is L cubed. So we got that. Okay, here I could replace this L cubed anytime I see it with volume, but let's not worry about that. That's the pressure for one particle. All right, well, what's the total pressure due to all the particles? Total pressure due to all the particles. Well, you just simply add up the pressures due to every particle, right? So we have n particles in this box. I'll just go ahead and add them all up. The pressure due to each one contributes to the total. 1, 2, 3, they all add up the same way. Well, okay, we can see that's going to end up being n times the average speed in the x direction squared. How's that working out? Well, what's the average speed in the x direction? Average speed in the x direction will be what? It'll be, and by the way, this is squared, speed squared. So x1 squared plus vx2 squared plus dot, dot, dot. Just go on all the way up to v, and then add, there's n particles. So when you get to the last one, that's n, and then divide by the total number. Now notice I can factor out the m in all these terms here. It's a common term. The mass is the same. So if I move this n to the other side over here, then n times the average velocity in the x direction is just the sum of all the velocities in the x direction. So that's all we've done here. Then is just replace all these guys with n times the average. Perfectly legit. Okay, so we're getting there. Now, what do we need to do? We need to use Pythagorean theorem in 3D, right? Because I mean, you can kind of see what we're going for, right? We figured out what the pressure is due to one particle, but we want to know now what the pressure is due to n particles when we fill up our box with a lot of particles, because that's the real situation for any ideal gas. So for all of them, we're going to be talking about the average speed. Okay, average speed. So for any given particle, its average speed is going to be the sum of its components. The average square speed is going to be the sum of its components squared, right? That's just the same as Pythagorean theorem um, in 3D. That's what it is, Pythagorean theorem in 3D, which you can see right here. Pythagorean theorem is c squared is equal to x squared plus y squared. So here's this right triangle. Then looking at that right triangle, um, z squared plus c squared is going to be equal to s squared, but meanwhile c squared is x squared plus z squared. So that's Pythagorean theorem in 3D. So if we're talking about the average speed of all the particles, then that's just going to be that's going to be the average of their components squared. And since every direction is the same for the box, there's no one preferred direction. The pressure on the walls is the same in any direction. That's got to mean what? The box is isotropic. There's no preferred direction in space. That means the average speed in any direction has to be the same. So when all particles are taken into account, on average, their speed in any given direction is the same on average. So that must mean then that, right, if these are all the same, um, say the y part and the z part all with x parts, right? Because every one of them is the same. So then the speed squared is 3 times the average speed in the x direction squared. Get rid of that. So what does that mean then? Just solving for the Vx, because that's what we had in our equation, in terms of the total speed of the particles is 1/3 of that total speed squared. Okay, so now we have our total pressure. It's the mass times the total number of particles times the average speed in the x direction squared divided by the volume, or L cubed. And now we can replace that Vx with 1/3 using the Pythagorean theorem in 3D. Plugging that right in over here, we get this. All right, so we got that. Using the fact that the volume is L cubed, we replace the L cubed with V, and we have the pressure is this. And moving the volume to the other side, we have pressure times volume is N times the mass times the speed squared divided by 3. Well, that's quite interesting. That's quite interesting. Now let's go back to ideal gas. With ideal gas, pressure times volume is N times Boltzmann's constant times temperature. But as we just showed, it's also N times the mass times the velocity squared divided by 3. Well, if this is true and this is true, then they're equal to each other. They both must be the same. Okay, and here we can cancel off the common factor of N if we like, and we get mass times speed squared average over 3 is equal to kT. Okay, but remember, we're trying to find T, proportional to the average kinetic energy, or equal to the average of 1/2 mv squared. Right, so how do we get that? So we have this now, but we want to get it in terms of that. So what do we do? Well, just look over here, just move a 3 onto this side and divide by 2, and then you get that. This is the relationship between kinetic energy and temperature, right? We started considering the pressure exerted by the combined particles bouncing around inside the chamber. But at the end of it all, using the ideal gas relationship, we got it the temperature in terms of kinetic energy. And this is exactly the relationship, right? 3 for an ideal gas, for a monatomic ideal gas, and that's pretty important here. It's just single tiny hard particles, non-interacting, 3/2 kT is equal to the average kinetic energy. Therefore, temperature is proportional to average kinetic energy. And we're at the end of the show.